Okay, welcome to the banks of the Wabash. My name is Stephen.
I'm Sarah.
Today we are going to do some hydrology. Hydrology is a big word though, isn't it, Sarah?
Hydrology is a big word.
So what do we really mean when we say hydrology?
Hydrology is water study. So it's looking at different things about the water. We're right here at the Wabash River, and we're going to be looking at some different things that we can do to take measurements of the water that we're observing.
Now, but before we actually measure the water, there's other things we have to look at, right?
Yes.
We have to, it's very important because when we're collecting data, because if we're not just looking at the water saying, okay,
Looks nice.
we're done. Woo, that was hard.
All right.
No,
not like that.
But we're actually collecting data. You always want to collect data when you go out and do some sort of research. And the thing about collecting water data is something a lot of people don't think about. We need to look at more than just water, don't we?
Well, what else are we looking at?
Well, first of all, time.
Okay.
The time of day. Because the water quality might be different in the morning, noon, and evening.
Yes.
Or middle of the night, which I don't test in the middle of the night. All right, so the time of day is important.
Okay.
And the date. What time of year? So they need to know the date. The time of day is important. But also our cloud cover, right?
All right.
Right? So we have to know that. Why do we want to know cloud cover?
Well, I think we want to look at cloud cover because it's going to affect how we view water transparency to start with. When we look at the water, how clear is that water? Well, the water is reflecting the sky. So we need to, like Stephen says, make observations about what's in the sky to start with, so that we have a reference point then when we start taking readings for the water.
And we have it's from the GLOBE program. We use their stuff a lot.
Right.
For a lot of our projects, we use the GLOBE, globe.gov, globe.gov. I'm not sure what I just said before that. I mixed it all together. So what they're asking, of course, the measurement time.
Okay.
And then they want to know what state the water is. And what they mean by that, is it about normal? Is it really flooded out?
Yeah.
Is it, what do they have? Is it really, is it dried up?
Yeah.
Is it dried up? No water there on the site? If you're testing a site a long time and all of a sudden there's no water there, scientists need to know that, right?
Yeah, they do.
Yeah, and then frozen, and then unreachable is the last one. Maybe it's a site, something's happening, we just can't get to it anymore, and that needs to be documented. The next thing we have is the sky conditions.
Yes.
So clear, cloudy, or obscured.
So let's talk about the difference between cloudy and obscured, because we know a clear sky when we see it. It's beautiful summer days, beautiful autumn days when there's no clouds, it's just bright blue. We've got that one.
Yeah, I see that now.
Yeah.
Oh, I see some clouds.
There's some clouds today.
There's clouds visible. There's some serious clouds way up there. There's some clouds.
But what if my sky is covered we have an airplane, so I don't know if that's going to affect it.
Well, we have an airplane in our sky. I wonder if there's a spot to write that down.
I don't.
There's a spot for contrails.
Well, there you go.
The contrails are condensation trails from jets, but airplane or a helicopter wouldn't have one.
Not
so.
one of those.
All right,
But
so,
if we have clouds completely covering the sky, is that obscured?
no, that's just 100% cloud cover. Because we could see the clouds, so they're not obscured, we can see them. Obscured is when we can't see the clouds. And so if, let's say we're in like a larger city area or something, and there's so much smog in the air, we always want to have our mask up then.
Yeah.
And there's so much smog, and it's, of course your air quality is poor, but you can't even see if there's clouds.
I see.
That would be. And there's instances like that. And you know what? Obscured, if there's ground level fog and we can't see what's going on, we count that as obscured too.
Okay.
Even though, fog's a ground cloud, right? Ground level cloud. We still count that as obscured. There's, you could go out to the absolute extreme and go with our volcanic ash.
Ooh.
If a volcano is close by and erupted and you can't see the sky because of the ash, just stay somewhere safe.
Yeah. We don't have volcanoes, so I'm not sure what to recommend that you do.
I've never seen one erupt in the Midwest in the U.S. here.
But we're guessing if there is a volcanic eruption near you, let's skip the cloud cover for today, right? We'll just go somewhere
Maybe
safe.
just go somewhere safe. But all right, so we're going to document what's happening around us.
Okay.
Right?
Yep.
And even if we're doing a long-term study, we're going to do a lot more than that, aren't we?
Oh, we are.
We'll map out, we'll draw out the whole thing, and we'll say what's close by, what's going on, and because all the things that impact the water itself.
The water, right.
And we took, right as we started, we took a 360 picture, didn't we?
We did.
And we'll post the link for the 360 picture so you can click on that and you can be able to look, and I want you to think about things that will impact the quality of the water. But as we talk about the quality of water, what are some things that we want to test? I want to test this water to get some idea of the water quality. What's some things we could test?
Well, we just talked about water transparency, so that's one thing. How clear is the water?
So water transparency, how clear it is, and that is very important.
Yes.
Here in Indiana, what's the number one pollutant in our waterways? Sediment. So we have places, actually right behind us you can see, we have places where it has eroded, and so then we see erosion. Erosion is the moving of sediment, right?
We can even see in those trees there. We can make those
we can see a lot in there. And we'll put pictures of the air, close-up pictures on the 360 if you want to look at it a little closer. And so it could be algae blooms blocking the transparency. It could be sediment suspended in there blocking the transparency. I mean, those are just some of the things that really impact the water quality.
Yes.
But why would that impact water quality? How well we could see through it? What's some things for transparency that changes?
Well, for one thing, the water temperature would change with water transparency.
Because we know that darker things will absorb more energy.
Yeah.
And so if the water is darker, instead of really clear, if it's really clear, it just kind of reflects a lot of the light. But if it's really dark, it absorbs the energy from the sun, and it makes it warmer. And that can be bad. That could be really bad and that leads us to another test.
That leads us to another test.
Temperature.
So with the temperature, right?
Temperature, yes. And you know what? If we're standing here and doing temperature, there could be, let's say this was runoff, because you can see there's a big grate there where it's probably a runoff when it rains and stuff, right?
Yeah.
The discharge.
Yep.
And so the water might be warmer right over there. Maybe it ran over a parking lot and it got warmed up. It's warmed up, we'll say it. It got warmer, and so then it gets into the water, and that changes it. And of course, different temperatures impact the ecosystem in different ways.
They do. One way, if you have warmer water, the fish aren't going to like warmer water as well, because fish depend on something called dissolved oxygen. Dissolved oxygen is what the fish run through their gills to breathe. They don't breathe in like you and I. They don't take breaths with lungs. What they do is they absorb the dissolved oxygen through their gills.
Yeah, but wait, water is H2O. Don't they just get that?
No, it's a different kind of oxygen. So that's correct. Water is H2O, 2 hydrogens and 1 oxygen. But between the water molecules, we have gas, oxygen gas, that gets dissolved into that water. And that's the oxygen that the fish need to live. And the cooler the water, the more dissolved oxygen that the fish will have. The warmer the water, the less dissolved oxygen the fish are going to have. So that's a test we can take. We can take a dissolved oxygen measurement there as well.
And there's other tests that we could do, like nitrates, phosphates and nitrates are tests that we oftentimes do when we do water quality. And that's, we get those, nitrates, oftentimes fertilizers would be one area we could get those. But another thing could be, oftentimes if it runs through an area that has a lot of decaying organic matter, then it'll pick up a lot of nitrates into the system there too.
Sure.
And it could be toxic levels, actually, of these things, is one problem with it. And another problem is you would get more plants and algae. Yeah, fertilizer is good for them. Yeah, and so, but if they overgrow too much, if there's too much of that, then again, it can be bad for our ecosystem.
Yes.
And so there's some of the tests that, we didn't talk about pH.
pH is another one that we want to measure. pH is a measure of how many hydrogen ions are in the water. And the more acidic something is, or the more basic something is, it can also impact the ecosystem. Water tends to be pretty neutral, so right in the center of the pH scale.
Pure water would be, right? Pure water would be. And really most living things like it fairly.
Kind of in that neutral range. Usually a pH between 5 and 8 usually is within range of something that that supports most ecosystems.
Yeah, once we get down into the 5s, we're getting acidic there, aren't we?
That's getting fairly acidic.
That's getting kind of acidic. It's going to be hard for fish and other aquatic life forms to live. And so we want that as close to neutral as possible. But lots of things could affect the pH, and so that's something we want to check to check the pH, and that is an indicator of water quality also. Is there any other tests that we have?
We talked about temperature, dissolved oxygen, pH, nitrates, phosphates. Is something else we can test? I think
That's kind of all of our tests, isn't it?
that's what we got.
I think that's what we have. And yeah, there's more tests that different people could take. They'll do flow rates and depths and all of those. But those just aren't tests that we're doing today. We're kind of doing what we consider more chemical tests to a degree, but I'm not sure if that's the right word really. But these are the tests that we've picked for overall indicator of water quality health.
There are, yeah.
Now, what we're going to do today is we're actually going to use some transparency tubes for our transparency. What we will do is we will fill this up. We'll rinse it out. We have to rinse it out a couple times, right? With the water we're testing. And here's the thing, if you're testing let's say you were testing this, and you were over here, you were getting ready to bend over, and I'm sitting here and I'm all excited. What's going to happen?
It's kind of, you might not be able to see it in this video angle, but his shoes have kind of disturbed the sediment at the bottom of the riverbed here.
Uh-oh, I just met... Oh, I got a lot of stuff moving around.
That's going to affect the transparency of the water then, and that won't necessarily be representative of what the actual water transparency is here.
Yeah, it's going to be a lot cloudier, isn't it? We're not going to be able to see through it. It won't be as transparent as it really is, so we won't know, will we? And so when you're working with people, you have to make sure that you're communicating with your group, and you have to make sure that one person isn't accidentally messing up your experiment.
Right.
And so what we would have to do is we will go, I'll step out further from where we weren't, since that's all washed over there. And what I'm going to do is just gently fill this up. Now I got to reach pretty far to fill this up, because just me walking over here, I'm going to rinse it and dump it downstream because the water's going this way. And so I want to do that a couple of times. Now the water's moving slowly enough, I'm having troubles with my setup. We'll get that out of the way. And I'm going to reach out just a little bit further. And I filled it up. Whoops, almost all the way. Got excited. All right, so I've filled this up.
And what we didn't show you at the beginning, there's a black and white disc at the bottom of this, and we'll show you a picture of this.
And we'll do close-up pictures in there, but this is just a long, clear disc. This one's sandy now. A long, clear disc, or a tube, and the bottom of it is a black and white disc. And this is a release on the bottom, so we can drain it. So Sarah's going to look through this.
What we're looking for when I look, so sometimes you look through and you think, well, this water's clear. I can see right through this, and you might be able to see, right? But when you look straight on, I can't see the black and white. I can't see the separation between the black and the white on the disc. So what we're going to do is we're going to work together. We're going to look.
You always want a partner. You always want a partner, and I will release. But as soon as she can make out that disc,
the difference between the black and the white sections,
she's going to say stop.
Okay.
And I'll close this up as fast as I can at that point. Okay?
Okay.
Ready?
Ready.
I'll let that come out.
Okay, stop. I can see the black and the white now at this level.
All right.
So the next thing we do, there is a scale here, and we're going to take a reading.
So where are we? There's 35, 36, 37. It's halfway between 37 and 38, it looks like.
Okay. And we see little marks for the ones place as well. And so, we see marks for the ones, and then we see marks for every tenths place, for every 2 tenths places. So we're going to say 37.6.
Yeah.
Yeah?
Yeah,
Okay.
37.6.
And that 0.6 is an estimation.
What is this measuring? Is that 37 elephants?
No, this is going to be 37 centimeters.
Oh, centimeters.
Centimeters.
I knew
so
there was a unit.
Uh-huh.
Now, we're not going to just write that. We're going to write that down.
We are.
But then we're going to retest it 3 times and then do the average of those 3, unless one of them was like way off.
Right.
Okay, if there's an outlier, we would just get rid of that data point because we did something wrong. But then we'll take the average and do this 3 times.
Yeah.
And so we're going to do this a couple more times and we'll be right back. All right, we have our dissolved oxygen set up, right?
Right.
And we've already talked about what dissolved oxygen is. We're using these ProbeWare, wireless ProbeWare, and that's just something that we'd happened to purchase and we're using for some of our stuff. And so rather than doing the other type of test, the chemical wet test that we have to do, this is just a lot faster and easier. And so we're going to do that. And to do that, we take and just dip our probe in. And Sarah has the app on the iPad, and so she will get our reading. So you got to do this as a team. What are we looking at, Sarah?
Well, before you put it in, it was right at about 6 milligrams per liter for dissolved oxygen, and it's still climbing, but it's getting close to, it's about 7.7.
But it won't do dissolved oxygen in the air, right?
Right.
And so we just need it to stabilize. So right now we're waiting for it to stabilize so that we can actually figure out what our reading is. And so it's going up, she said.
Yep. Starting to taper off.
What are we at right now?
Right now we're at 8.35 milligrams per liter.
Okay.
Still increasing.
Now, we'll record this data, and we'll do this 3 times. Like all of our experiments, we do it at least 3 times. And once we do it at least 3 times, then we'll take that average. And that way, if we're a little off on one, and like I said, unless there's an outlier. And so, all right, what is our, can you do a screenshot and get our reading?
Yep,
All right.
screenshot.
What is our final reading?
Our final reading is 8.64.
8.64 is what it's going to be.
And that's in milligrams per liter of dissolved oxygen.
Milligrams per liter, that's our unit. We always want to label with our units, don't we?
We do.
I'll put this back in here, protect this. And so that's, we'll go ahead and do our 3 measurements. And after we do our next 2 measurements, we'll come back and we will do pH next. Now we're going to do our, this is pH, right?
pH, this is going to test pH
Our
now.
pH. We have to be careful, I know, with these because it's like a glass bulb on the bottom of that. And so we have to be careful not to actually hit anything.
That's right.
And some people, I've had people ask, well, what is that in? This is what we call a buffer solution. And that's so that bulb knows, oh, this is a 7. That's exactly what we want. Or sometimes it's a difference. Sometimes it's higher or lower. But
I think this buffer solution, I think, holds at about a 4.
A 4. This is a 4. Okay. And so it's a buffer solution. We don't want to pour that out and contaminate anything. So I'll just drip that out real fast so all that's out. And then I will pick our site just like the other times. Same spot because this is our area. I'm going to swirl that around for a minute or 2 here. Not violently, but just kind of mix it around. And Sarah's collecting. It's nice when you have a team, a group being able to do these things. And so one person can step into the water and the other person can keep her feet dry. Although Sarah never keeps her feet dry.
No, right now the pH has reached 8.02.
Okay. Is it stabilizing?
I think yes, it just kind of stopped at about 8.15.
All right, get your screenshot.
Yep.
And what'd you say it was?
8.2.
About 8.2. All right, so what I would do is put this back in here so we're protected and we don't spill our buffer. And then I'm gonna put that back somewhere safe. But we're not done because sometimes you don't have the probes, right? Some people don't. And what we always used before that was test strips. There's all kinds of test strips that different programs use.
Right.
And so this test strip is just a little bitty piece of like a plastic that has something on it. And what we have to do, we have to put it in the water for 10 seconds, waving it around. 4, 5,
So the little pieces that are on there have something called an indicator, and the indicator changes color with a pH change.
You keep it out for 20 seconds.
Okay.
1, 2, 3.
So what Stephen's going to do when it hits the 20 seconds is he's going to match it up to this color chart that we have on the bottle. And that way we're going to be able to compare the colors that are indicated on this strip from being in the river to the color chart that's on the bottle. And then that's going to help us understand what the pH level
Now,
is.
this isn't going to be quite as precise as
No,
the
right.
other one. But here, on this one, as hopefully we see in the picture, hopefully I have a nice spot, we can see it's not quite dark enough at the top to be 8.5, but it's a little darker than at 8. So somewhere between 8 and 8.5 is what we got.
And that's really good because what we received on our probe when we took the pH reading with the Vernier sensor was 8.2. So I agree with between 8 and 8.5.
Yeah.
I think that
And
makes a lot of sense.
I would put down if it's closer to one, slightly closer maybe to 8. And so, I mean, I would call this, I tell you, I would probably call this an 8.3 because it's slightly closer to the 8.5 on this. So I would call this test an 8.3. And so that's what we would record.
This is more of a qualitative measurement because it's based on a color that you're perceiving, whereas this is more, with the probes, more of a quantitative measurement because we're getting an exact number.
It's just the probes are more precise, and so if we're doing precision and stuff, we would want to try to use a probe. But if for most things, this is pretty close. This is 0.1.
Yeah.
And so this is really close enough. And if this is what we have, and we're using these, then we want to test it with this next time. And so let's say we're seeing what the pH is every day this week.
Okay.
We're doing a project, seeing if it's changing through the days. And so we would always want to use the same type of thing to test, the same instrument. And that way you know that you're getting consistent results. Because all instruments, whether it's a fancy digital one or something like a paper test, there's going to be a degree of error.
Yes.
And so we want to make sure that we're being consistent in our experiments. And that's with anything we do. Okay, Sarah.
Yep.
We put away our other instruments, and we got our thermometers.
Got our
I know
thermometers.
you have one of the Vernier probe
Yep.
thermometers in the iPad, but I brought these thermometers.
Nice.
And so, because I figured a thermometer's a thermometer, it won't
That's
matter,
exactly
right?
That's exactly right.
Any thermometer should work. Now, what's our air temperature? That's something. Oh, we got to shade it with your body,
Oh,
right?
right. Yeah. Hold
Shade it with your body,
Yep.
so the sun's not affecting it. Live here for a minute. Then what's the air temperature getting to be here?
Mine's reading right at 29 degrees Celsius.
29 degrees Celsius.
29, isn't that like winter? 29 degrees Celsius?
Whoa, no.
No?
That's not winter. That'd be 29 degrees Fahrenheit. Would be winter.
Oh, so Celsius.
We use Celsius in science.
That's right. We use Celsius in science because all over the world, most places, most scientists, when they're taking data, collecting data, and reporting that data, they're reporting it all in the same unit, and that's Celsius.
Right.
And we're not used to Celsius degrees here in the United States. We use Fahrenheit. So Fahrenheit temperatures make more sense to us because we probably hear them on a daily basis. If you're riding to school, right, and you hear what the temperature is going to be on the radio maybe, or you see it in the newspaper, or maybe you even talk about it in your class at the start of the day. But with Celsius, it takes our brains a minute to think about, well, what does that mean in terms of Fahrenheit? So we have a really quick way that will help you kind of think about what a Celsius temperature might mean to you, and that way is we're going to say 30 is hot,
30 is hot,
20 is nice,
20 is nice,
10 is cold,
10 is cold,
0 is ice.
0 is ice.
So right now
I like
it's
that.
29 degrees Celsius. It's pretty warm today, isn't it?
Oh yeah,
We're dressed. I mean, we're in short sleeves and shorts because we're right here. I can feel the heat. Right, I can feel the reflection of the sun off the surface of the water.
It's
now 20 degrees. If you're sitting in your classroom, that you're probably closer to 20 degrees. That's usually about room temperature if you're indoors and you don't have the sun shining through a window. If you're just indoors and there's just room lighting or whatever, usually that's right around 20 degrees Celsius, and that's a nice, comfortable temperature.
Yeah.
10 degrees is if we're getting ready to get into fall. If you have a really chilly fall morning, you need a coat, right? And then 0 degrees is where we see it's the freezing point, melting point of water and ice. So 0 degrees is where water freezes.
All right. And so
As
for
we're taking
your data collection, you can use the alcohol-filled ones, but you need to calibrate them. And so I did not calibrate this one, so I'm not going to be able to use it today because we really don't know what the actual measurement is. So we're just going to be able to take our temperature with Sarah's. The digital one, we've calibrated all of those, and so we know it's calibrated correctly. And so we're just going to use that one today. But next time, I'm going to calibrate, I'm going to fix that one that's separated, and I'm going to calibrate both this one and that one, and I'll put a tag on them that tells me what the calibration is. And you'll have to watch that video if you want to go ahead and calibrate yours. We'll walk you through how to do that. So, all right, let me put this down.
Okay.
And I'll get this.
Okay.
And so, all right, we want to get our temperature.
Yep.
And so, I'm going to put this right down into the water, a few inches, because it reads
And it's
off the
dropping.
tip.
Yep.
No, the temperature drops, so it's cooler than the air.
Yep. The water's going to be a little bit cooler than the air right now.
It's a bunch of little minnows or little fish trying to bite my thermometer.
I see them. So it's just dropped a full degree. We're down to 27 degrees Celsius.
Oh, we're going
Or
to have
2
to
degrees, I guess.
probably wait a couple minutes here for that to settle, aren't we?
That's right. And actually, when we take our temperature reading out in, like, just out here, out at the river, the protocol is you would wait 3 minutes.
Ah, okay. So we'll wait 3 minutes before we actually and let it settle and figure out what it really is. I love being out on the river. I see birds and all kinds of things, the little fish.
Sorry, there's all kinds of minnows swimming around. That's really neat. Now we say 3 minutes, but if you notice that the temperature is not changing anymore.
Yeah, if it's just staying still, we can go ahead and record that. All right, so what's our measurement?
So right now it's staying really constant at 26.8 degrees Celsius.
And
it's
you want to do a
not
screenshot for that? So
Yep. I think the screenshot, it flipped to 26.9 right as I said that.
All right.
Again, that last reading that we have, the last number in your measurement, especially with the temperature, is going to be just an estimation. So if it's 26.8 and then all of a sudden it changes to 26.9 and then it goes back to 26.8, that's the digital device just taking an accurate reading, and it doesn't matter, that last digit, it doesn't matter if it's 0.8 or 0.9.
Okay, good. Now,